so starting from the beginning, number fields. The notion of a number has been formalized in mathematics rather early on. This goes back to the late 18th, early 19th century, when mathematicians started thinking in rigorous terms about what their mathematics means. They called a set of numbers a field, nothing to do with physical fields like magnetic fields, so this is mathematical field. And a field F, let's call it F, is a set of objects with an addition operation and a multiplication operation such that. And here I will start introducing some new notation of the kind that you may not have seen at school or you may not have seen in your previous courses. So here we will have notation. First symbol that mathematicians often use is this inverted A. That means for any. The other symbol that we will now use is something that looks a bit like the Euro symbol. Means belongs. And so, we can start writing the conditions here. So A. For any number A and number B belonging to F. So you can see the brevity of that notation. We must have A plus B belonging to F and A times B belonging to F. So if we take any two numbers that belong to a certain field, like real numbers, their sum must also belong to the same field, must also be real, and their product must also be real. In a way, a trivial observation, right? If we take two integers, their sum is an integer and their product is an integer. If we take two real numbers, like 1.5, 2.7, their sum is also a number of the same type. Less obviously, and here we need to introduce another item of notation here, exists. For any A belonging to F, there must exist an inverse element. There exists a unique inverse element called A minus 1, such that A times A minus 1 is equal to 1. An inverse must exist. We can easily find sets of numbers for which this is true. If we take, for example, a set of all real numbers, then, well, if A is 3, then A minus 1 is 1/3, and so 3 times 1/3 is 1. If we, however, take integers, only integers, we can have a 3, but we cannot have a 1/3, because 1/3 is not an integer. And so, into this A and B conditions, real numbers, rational numbers do fit, but integers already don't. Right? So the real numbers are a field, but integers are not. Let's see. For any A belonging to F, there must exist a minus A, such that A minus A is 0. Again, an apparent triviality, but the reason why we are putting this in such a rigorous way is that in this course we are showing you how mathematicians think about these things. So something like a definition of a number might not strike you as particularly important initially, but when we start moving to quantum mechanics in your second and third year, where complex numbers are the norm, but it begins with complex numbers, these things will start to matter. And also they put your brain into a kind of order that you need to be a scientist. Okay, D. There must exist a unique unit element and a unique zero element inside F, obviously. various other minor things. So bracket rules, like how you are opening brackets, must be observed. And I think that, no, there's another rule, F, for any A and B belonging to F. A plus B must be equal to B plus A, and AB must be equal to B. So the order of the operations should be obviously observed for the numbers that we usually see, but not observed for rotations. Not necessarily commute. And so that is a definition of a number in mathematics. So let us now look at a few examples. Here, examples. Real numbers are, well, clearly for any two real numbers, their sum is real, their product is real. For any real number, the inverse exists, just 1 over. The negative clearly exists. There is 1 and there's 0, and they're both real numbers. Brackets are clearly followed, you can demonstrate it explicitly. And we know that for real numbers, A plus B is B plus A, and AB is BA, so they are affiliated. If we look at all integers, both positive and negative, this is true. That, however, is not true, because there's no multiplicative inverse for an integer, because 1 over integer is not usually an integer. So, no. Rational numbers, pure. They are numbers of the type A over B, where A and B are integers. Sum of two rational numbers, well, we know how to add fractions, is a rational number. Product is as well. For any rational number, an inverse does exist, which is small a and b. In here, negative clearly exists. There's a 0, there's a 1, and these are followed, and brackets are observed, so rational numbers are affiliated. And finally, we come to the topic of today's lecture, the strange constructs called complex numbers. And as we will see in the course of our lectures, complex numbers are affiliated. Now, for the first year students present, second and third years are probably quite comfortable with complex numbers by now. Real numbers, 1, 2, 3, 4, 5, 2.5, and so on, are not how the universe works. The deeper you go into complicated topics like general relativity, electrodynamics, even Maxwell's equations, quantum mechanics, and so on, the more you realize that it is in fact complex numbers which are fundamental to how the world is running. Reasons are complicated. It has to do with the fact that fundamental interactions are always two-particle, and so you need an object with two variables in a way, because fundamental operation is a certain type of rotation. If you look at the equations of motion, in quantum mechanics, the very equations of motion, the equivalent of F equals ma, is complex valued. And the most fundamental function we know of that describes how chemical systems work, in particular, always the wave functions. The wave function is complex valued. So far from being exotic, incomprehensible, that we certainly are, but far from being exotic, the complex numbers are common. It's just within our evolutionary history as humans here on Earth, we have never encountered phenomena of that kind. We were hunting mammoth, right? And I mean, Homo sapiens is just in its latest form, is just 100,000 years old as a species. So we haven't seen them in our evolutionary history. It's only been 100 years or so since we've really seen them as a species, and so they're a bit unusual, but very fundamental nonetheless. So, the definition of a complex number. Complex numbers. In may have noticed certain old-fashioned kind of teaching in here. I do not use PowerPoint, and you will see soon why mathematics cannot really be taught with PowerPoint. You have to follow things through. The other sort of strange feature is you will catch me multiple times making arithmetical mistakes. Somehow it is singularly hard to do arithmetic in a foreign language. And so please forgive me when you see me floundering then. Okay, a complex number. Is the following construct. A plus IB, where A is real, B is real, and phi squared is minus 1. They initially arose in the works of Cardano and company in Italy, 18th century if memory serves, as formal solutions to algebraic equations. Cardano noticed that an equation of a type, x squared plus 1 equals 0 is not apparently different, at least visually, to any other polynomial equations. Yet he couldn't find solutions, except by introducing this strange quantity I. And so initially it was in a way an exercise in bringing mathematics to order, in that they introduced it almost on aesthetic reasons. They said, oh well, this strange construct enables us to solve any possible polynomial equation, so why don't we have it? As it often happens in mathematics, what is beautiful is in fact what is true. And they just catch on, and then it transpires in modular physics. So they are added and multiplied in the usual way with this little specificity. So if we take A plus IB and add to it C plus IB, we just literally add them algebraically and do the rest. So it's A plus IB plus C plus IB. Why don't we take I out of the bracket here? So it's A plus C plus IB plus D. Right? So you just add the real part and add the imaginary part, where the real and the imaginary parts are defined in the following way. So the real part of A plus IB is A, and the imaginary part of A plus IB is D. Imaginary is an unfortunate term here. They're no less real. You can take my word for it. But the name's called. Okay, multiplication. The usual bracket opening rules. So A plus IB, C plus ID. Multiply that by this by this, so it's AC, plus this by that, IAD, I is conventional in front, ID, this by this, IDC, and finally ID times ID, I squared B. I squared is minus 1, so that is real, that's imaginary, and that's imaginary. So it is AC minus BD. That's the real part. And then AD and BC plus IAC plus BC. So far so good, and all of you who read the A-levels had at least this in the final parts of your courses. Fractions are a bit less obvious if you have A plus IB divided by C plus IB. You would often be asked to simplify it. And for this, we need to introduce another definition which is specific to complex numbers. So that's the real, that's the imaginary, and now the concept of conjugation. star, it is denoted by a little star. And that simply means that all instances of I change sign. So it's A minus B. This also applies to complicated functions. If we have something like, I don't know, exponential of cosine of A plus B, the complex conjugate of this crocodile is still the same expression with all the i's changing sign. So exponential of cosine of A minus I. So when you see the star operation, that simply means you have to solve the sign of I. Okay, so the trick here, when you are operating on a fraction, is to multiply both sides by the conjugate of the denominator, and we will see in a moment why that is the case. So, let's try it. For now, it's one attempt. C minus ID, C minus ID. So, for no reason in particular, I've just decided to multiply and divide the fraction by the conjugate of the denominator. Let's see what happens. So, something complicated appears in the numerator, so that's K plus ID, C minus ID. And then in the denominator we have C plus ID, C minus ID. Let's try simplifying it. We'll leave the numerator, well, okay, let's open the numerator. So, AC minus I A D plus I D C. And here we've got plus I minus I, so minus I squared B. In the denominator, we would have C squared minus ICD plus ICD, and then minus I squared D squared. But look, denominator simplifies quite significantly. ICD with a minus, ICD with a plus, they cancel. I squared is minus 1, cancels with this minus. And so we have here AC, this I squared destroys that minus, plus BD, plus I BC minus AD. And in the denominator we have C squared plus D squared. The simplification here is we have no I anymore in the denominator. The denominator became real. And so we can now split this out into the real and the imaginary part. So we have C plus BD C squared plus D squared, and that's purely real, plus I BC minus AD C squared plus squared, and that's purely imaginary. So we have split out what was initially a fraction into its real part and its imaginary part, and we simplify it. Now, theoretically, one would, of course, remember this rule, that this particular complex fraction gets simplified like that into a real and imaginary part, but it is actually unrealistic to remember it. What is realistic to remember is when you are seeing a fraction, you should multiply and divide it by the conjugate of the denominator. And then run the simplifications, and the thing will simplify, and we will now go through some numerical examples of what you do with it. Any questions so far? So all of that is on video. The video will be on YouTube in high definition, and you will have the link posted to your what's it called, Blackboard system. This handout will also be there. You may have seen it already. Again, the third years, particularly chemistry and math, have seen this already. Bear with me. Just be bored for a couple of lectures, and it will get interesting. I promise you. We've made sure it does. Okay, examples. by now why I'm not using PowerPoint. If I had flown through this on a PowerPoint slide, none of you would have remembered or understood it. Right? Slow-paced writing gets mathematics across. Okay, so let's say 2 plus 5i times 3 minus 2i. Open the brackets, multiply up. Remember that I squared is minus 1. Nice and easy. So 2 times 3, 6. 2 times minus 2i minus I. 5i times 3, 15i. 5i times minus 2i minus 10i squared. Minus 10i squared is plus 10. And 6, 16. 4i, 15i, with different signs, plus 11. Addition is even easier. So 2 plus 5i plus 3 minus 2i, just element by element. 2 plus 3, 5. 5i minus 2i plus i. Fraction, that's going to be a bit of a long story. So 2 plus 5i over 3 minus 2i. Okay, as per our recipe, we need to multiply and divide by the conjugate of the denominator. So 2 plus 5i, 3 minus 2i. The conjugate of the denominator here is 3 plus 2i. 3 plus 2i. 3 plus i. So because we multiplied and divided by it, the fraction shouldn't change. But what will happen is some simplifications will appear. And so that's 2 plus 5i, 3 plus 2i. In the denominator, 3 minus 2i, 3 plus 2i. Just opening the brackets here. 6, so 2 times 3, plus 4i, plus 15i, plus 10i squared, over 9, 3 times 3, 3 times 2, you've got 6i, minus 2 times 3 minus 6i, so the complex, the imaginary part cancelled, and then minus 4i squared, which is just plus 4. Okay, simplifying the numerator, that's 6 minus 10, so minus 4, plus 4i plus 15i, so that's 19i, divided by 6i minus 6i got cancelled, 4i squared, popped a minus in front, that became a plus, over 13. And if I haven't made any arithmetical mistakes in there, and I haven't, good, that's minus 4 over 13, plus I times 19 over 13, and that would be the final answer that you would be required to produce in the exam if we ask you to simplify the structure. Okay, so this is the definition, and these are the basic properties of complex numbers. There's one interesting connection to geometry, and particularly to rotations. You would notice here that a complex number, in a way, is a two-element object. It has two independent real numbers in it. Turns out there's a geometric meaning to that. That is sufficiently important that most computer games these days, when they do rotations, and they have to do rotations at an extraordinary rate. When you are shooting up monsters in some, I don't know, Doom 4 Well, here again, you are looking at polygon monsters, and those have got millions of vertices and millions of faces in those polygons. And so you are shooting them at 60 frames per second, and so you can try and calculate how much mathematical firepower that requires. You need to rotate several million polygons, each of them with 3 vertices, at 60 frames per second. So conservatively speaking, 10 million rotations, 60 times per second. So it's 600 million rotations per second. That's a lot, and I will now show you how that's actually done in a computer, and that's done using complex numbers. So, consider the following, as mathematicians call it, map. A plus IB. It has 2 independent numbers, A and B. Let us consider that will be our Z, it's a complex number. Let us consider a vector R with elements A and B. On the surface of it, that's a scalar with something strange attached to it. That's the usual 2-dimensional vector that we know and love. What can there possibly be that has them in common? Well, let's take a look. So if we have our R in here, so for R, we have, of course, the modulus that you know from standard geometry is A squared plus B squared square root. And we have the angle that it makes with the x and the y axis. And the usual convention in mathematics, and this is something that you will encounter time and again, so if we take, if you remember that now, x and y, we have a vector R. It has the x component, the y component, and it has this angle phi. This is the so-called polar system of coordinates. You have your x and the y, but you can also specify the point location with r and phi. And phi is counted counterclockwise from the x-axis. Don't ask me why. Somebody in the 16th century decided it should be that way and just stuck. So phi counterclockwise from x. And all rotations in mathematics and physics, the positive rotation is counterclockwise. Again, somebody has to make a decision at some point in history. We just made it and we are stuck. So, if we look, we've got the modulus and we've got the angle, phi, and if that's our x component, so this would be A, and that's our y component, that would be B, then we know that the tangent of this angle from basic trigonometry is the far side divided by the near side, and so the angle itself is the arctangent of B divided by A. Why don't we introduce the same notation for complex numbers? We will introduce something called the modulus of the complex number. In the case of real numbers, that simply means knock off the minus if there's any. In the case of complex numbers, that means doing the same thing as the length of the corresponding vector. So square root of the real part plus the imaginary part with squares. And we will create something called the argument of a complex number, and we will also call it phi, in exactly the same way. Arctangent of B over B. What use can we possibly extract from mimicking the behavior of vectors with complex numbers? In a sense, I've just taken something that you know already about geometry. I've taken a simple 2-element vector and I put it as a length and an angle. What do we possibly stand to gain by applying the same sort of mathematics to complex numbers? Well, let's take a look. If we go back into this original Z, we remember from the Cartesian coordinates that x was r cosine phi and y was r sine phi, right? And so we can rewrite our original z as its modulus times cosine phi for the real part, because that's a, and sine phi for the imaginary part, multiplied by the sine. So this is called the polar form. Of a complex number. That, however, starts looking like a rotation. Right? You see a cosine phi and a sine phi, and in a moment we will make a connection and see why computers find it so much more efficient to execute rotations in this way than by using explicit sines and cosines. So, let us take a look at that strange combination. Cosine phi plus I sine phi. It was discovered by Leonhard Euler when he was working in St. Petersburg Academy of Sciences, and it has a pretty fundamental significance. And why that is the case, we will now see. If we open a book and ask, scroll it to the place where it has power series for the functions, the book will tell us that cosine phi is 1 minus phi squared over 2 factorial plus phi to the fourth over 4 factorial minus phi to the sixth over 6 factorial, and so on. Where the factorial is a product of all the numbers up to that. So 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. Right, so pronounced not 6, but 6 factorial. Similar for sine, except it has all the odd powers. So it has phi minus phi cubed over 3 factorial plus phi to the 5th over 5 factorial minus phi to the 7th over 7 factorial, and so on. And we multiply it by I and I, so that gets a phi in here. Let's take a look. If we have all the even powers for a cosine and all the odd powers for a sine, if we just sum them together, we will have all powers completely. And notice this alternating sign. Whenever there's a minus, we can put I squared into them and make it a plus. So once we do all of this, we actually discover that cosine phi plus I sine phi looks like the following. It's I phi to the power 0 divided by 0 factorial, which is 1 by definition, plus I phi to the power 1 divided by 1 factorial, plus I phi to the power 2 factorial, plus I phi to the power 3 over 3 factorial, and so on, all of them. And we then look into the reference book again, and we discover that e to the x has a very similar power series. It's x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial, and so on. So in fact this, if we take this into account, simplifies massively into e I phi. So what I just gave you is an example of a derivation. I have something at the beginning, I looked up in a book the expressions for that, I rearranged those expressions, and I arrived at a massive simplification. Of course, it is impossible to initially guess where to go, but I could have simply just given you that formula, you would have to remember it, in which case you probably haven't had much understanding of where it comes from. And the point of this course in particular is to actually provide you the origins of everything you know. And so that is, by the way Euler originally derived it. And so our conclusion that e to the I phi is cosine phi plus pi. Sine phi is known as Euler's law. Let us put phi to a particular value. I think it's pi. So if the angle is pi, e to the I pi is cosine pi, if memory serves, is 1, right? Or minus 1. Pi minus 1. Minus 1. Sine pi is 0 plus 0. And that we can rearrange into e pi pi plus 1 equals 0, which has all the fancy, strange objects you've ever had in numerical mathematics in one equation. You have the e, the natural logarithm base. You have this exotic I, which is root minus 1. You have pi, which is also an irrational transcendental number, which was slightly mysterious, at least to the ancient Greeks. You have 1 and you have 0. Right? So this is a particularly beautiful relation that illustrates the deep connections between all of these exotic numbers. But how does all of this relate to a rotation? Well, notice we have cosine and sine in here. So let us take some function. In the case of a computer game, this will be a three-dimensional monster, but in our case, we have to make do. It's something slightly simpler, so I'll just produce really some random looking function. And let us see what happens to it when we multiply it by a complex number. Right, so some arbitrary looking function f of t such that the real part of f of t would be 16 sine cubed. It's just a random function. I just pulled it out of the book without thinking too much of it, but it's how it transforms that will be interesting to us. And the imaginary part of f of t will be 13 cosine t minus 5 cosine 2t minus 2 cosine 3t minus cosine 4t. If you plot it on this Cartesian diagram, it's called Argand diagram, by the way. So that's the imaginary part. That's the real part. And you plot both the real and imaginary as a function of t. So implicit plot, it's sort of a fancy heart-shaped function. And that's 5. That's minus 15 there. Minus 15 and 15. So just a curve in 2 dimensions. And let us now multiply this function by some complex number. So we will have a, the amplitude, cosine phi plus I sine phi times this function. So 16 sine cubed t plus I, and I will not rewrite this long imaginary part, so that just goes into here. You have all of that in your handouts, so that you can simply just download. Okay, so let us multiply this out. Cosine times that, so a overall, and then cosine phi times 16 sine cubed t plus I sine sine ut plus I cosine phi times the bracket, and then I minus sine phi bracket. This doesn't look like much until you start thinking about it. Look at it. Our real part got multiplied by a cosine, and it got multiplied by the I sine. So the real part stayed real with the cosine. There appeared to be a little bit of the imaginary part with a sine. The imaginary part stayed back with the cosine, and a little bit of real with the sine appeared. What this looks like is a standard rotation that we have seen many times at school, when we have x prime equals x cosine phi minus y sine phi, and y prime is x sine phi plus y cosine phi. So this sort of rotation you've already seen. And so our real part, which is here x, got multiplied by the cosine, and a little bit of imaginary part, which is y in our case, arrived with the sine. The imaginary part got itself a little bit of the real part, the original real part with the sine. So there it is. And it has stayed back with the cosine here. So this is in fact a rotation. Y phi. Now, so if we redraw our plot here, what we will see is that the entire function got itself rotated. By an angle phi. Why would this be beneficial to a computer? Think about it. If we were to do the rotation this way, we would have to calculate a cosine and a sine. A cosine, mathematically, is a very expensive operation. You have to take 1 minus square, so it's multiplication. Then you have to compute the factorial. That's a bunch more multiplications. Then even more multiplications, To converge this series to machine precision, you need a couple of hundred multiplications at least. You would have to calculate the sine, that's another couple of hundred multiplications. You would have to put them together, add them together. So let's say we're talking about 300 or 400 floating point operations in total. If you are doing a rotation by just multiplying it by a complex number, you need to do no more. And what we did there. So I had 4 multiplications in total before. So suddenly, instead of doing it trigonometrically, if you do it via complex numbers, you have cut down the calculation time by a factor of 100. And so that appears to be essential in more and high performance computing, to the extent that doing it, the school way is not only detrimental. Every textbook on numerical computing tells you specifically avoid ever computing trigonometric functions. Do it that way. You can do various other efficiency tricks here, but this is, I guess, a relation to something that you can instantly recognize. That's all. It's on your desktop. So every time something rotates on your screen on the computer, it's not sines and cosines, it's the complex numbers that are being multiplied under the body. Right. Anything else that I've got to say for today? Yeah, so there's one last example where we separate the function into its real and imaginary part, because that's going to occur during your philosophy. I think one class is tonight, the others on Friday. separate 1 over 1 plus I omega into real and imaginary parts. This is a frequency response function of an electrical oscillator, by the way. You will see these things in electrochemistry, where impedance is defined as the resistance plus I times inductance. So, fairly frequently encountered curve. Okay, well, we do it in the same way as what we did for the fractions. That's a simple but impact fraction. So we multiply and divide by the conjugate of the denominator. So 1 plus I omega equals 1 plus I omega, 1 minus I omega, 1 minus I omega, 1 minus I omega over 1 plus I omega, 1 minus I omega, opening the brackets in the denominator, 1 minus I omega, 1 minus I omega plus I omega, minus I squared omega squared. This cancels that. I squared is minus 1. 1 minus I omega. 1 plus omega squared. The denominator became real. That means that is 1 plus omega squared minus I omega 1 plus omega squared. That's the real part. That's the imaginary part. And you have separated the two, where previously you had a complex number in the denominator, and it wasn't clear which part is real and which part is imaginary of this expression. Again, modern digital computers cannot manipulate complex numbers directly, so they store them as pairs, real, imaginary, and then combine them in the right way when the time comes. That's all I have to say today. Any questions?